If you look up at the sun on a clear day, you are staring at the engine of the stars. For 4.5 billion years, our sun has performed a miracle of physics. It does not burn chemical fuel like coal or gas. It crushes the lightest elements in the universe together. To understand the scale of the challenge in replicating this, we have to distinguish it from the nuclear power we use today. Fission, the process behind every nuclear plant operating on Earth, is an act of division. It requires taking massive, unstable atoms like uranium-235 and breaking them apart with a stray neutron. While effective and dense with energy, it carries baggage. It relies on rare, toxic elements, carries the risk of a meltdown, and leaves behind radioactive waste that remains hazardous for tens of thousands of years. Fusion is the exact opposite. It is an act of creation, taking the lightest, most abundant atoms in the universe and forcing them to marry. A fusion reactor cannot melt down. If the conditions change, the reaction simply flickers out in a fraction of a second. It produces no long-lived radioactive waste. Its primary fuel can be extracted from ordinary seawater. It represents a path to carbon-free energy at a planetary scale. And right now, inside nondescript warehouses and university basements, a quiet race is underway to build a star in a jar. But getting atoms to fuse on Earth means fighting a fundamental law of physics. The universe has strict rules, and atoms, by their nature, do not want to touch. At the center of every atom is a dense nucleus carrying a positive electrical charge. If you try to push two atomic nuclei together, they repel each other violently, acting like the identical poles of two powerful magnets. This is the Coulomb barrier. To overcome this barrier, you have to unleash the strong nuclear force. But this force only activates when two nuclei are brought within a trillionth of a millimeter of each other. In the core of the Sun, the crushing weight of gravity does this work, compressing hydrogen atoms at 15 million degrees Celsius. On Earth, we lack the massive gravity of a star. To make fusion happen here, we have to find a shortcut. Instead of ordinary hydrogen, we use two heavy isotopes, deuterium, which is stable and abundant in water, and tritium, its radioactive sibling. But the right fuel is only the first step. Lacking gravity, engineers have to force the reaction using extreme heat. When you heat deuterium and tritium gas, the thermal energy causes the atoms to vibrate so violently that they tear themselves apart. Their electrons are stripped away from their nuclei. What remains is a swirling cloud of charged particles. This is no longer a gas. It has transformed into the fourth state of matter, plasma. To compensate for the lack of gravity, we must heat this plasma to 100 million degrees Celsius, 10 times hotter than the center of the Sun. At that temperature, the nuclei move at such velocities that they smash together, shatter the Coulomb barrier, and fuse into helium. In that microscopic fraction of a second, a tiny amount of mass is erased from existence, converted into a burst of thermal energy, exactly as Albert Einstein predicted with E equals mc squared. The mathematics of this process was confirmed decades ago. We first proved we could create a star on Earth in 1952 with the Ivy Mike detonation. But that was a bomb, uncontrolled fusion. For power generation, the obstacle is containment. How do you hold something that is 100 million degrees? Any physical material known to science will instantly vaporize if it touches the plasma. Because plasma is electrically charged, it responds to magnetic fields. This allows scientists to use invisible force fields to cage the superhot matter in a vacuum, holding it in midair so it never actually touches the reactor walls. In the early 1950s, American astrophysicist Lyman Spitzer envisioned a twisted tube wrapped in magnetic coils to achieve this. He called it the Stellarator. Meanwhile, Soviet physicists Igor Tamm and Andrei Sakharov designed a donut-shaped magnetic cage called the Tokamak. The Tokamak design was more effective at trapping heat and became the global standard. Governments poured billions into building these machines, believing that clean energy was just a few decades away. But they fundamentally underestimated the wrath of a captive star. When you try to trap the fire of the cosmos, it does not sit quietly in its cage. A burning fusion plasma is one of the most hostile, unpredictable environments in the known universe. To understand the nightmare that engineers awoke to, you have to look at the subatomic debris left behind by the reaction. When deuterium and tritium successfully fuse, they create a helium nucleus, but they also spit out a rogue, high-velocity particle called a neutron. 80% of the energy generated by a fusion reaction is carried away by these flying neutrons. Here is the core physical obstacle that engineers have been battling for over half a century. Neutrons have absolutely no electrical charge. Because they are electrically neutral, the massive magnetic cage holding the plasma at 100 million degrees is completely invisible to them. The magnetic fields cannot trap them. The neutrons fly straight out of the plasma core, like subatomic shrapnel, traveling at thousands of miles per second, and slam directly into the physical walls of the reactor. Over time, this intense, relentless neutron bombardment completely alters the atomic structure of the metal. The steel becomes brittle, physically degraded, and highly radioactive. You have a machine that is violently and continuously destroying its own containment structure while it operates. This degradation is only the first problem. The second is the fuel supply. While deuterium can be pulled from ocean water indefinitely, tritium is incredibly rare. Because it has a radioactive half-life of just 12 years, it decays quickly. There is naturally almost zero usable tritium on the entire planet. To make a global fusion economy work, reactors will have to manufacture their own fuel while they burn it. The proposed solution is to line the inner walls of the reactor with a thick blanket made of lithium. When those high-speed rogue neutrons escape the plasma and smash into the lithium blanket, a secondary nuclear reaction occurs. The lithium atom absorbs the neutron and splits, creating a brand new atom of tritium fuel. This freshly bred tritium must then be siphoned off, filtered, and fed directly back into the plasma core to keep the fire burning. It is a delicate, closed-loop balancing act. The reactor must function as a furnace, an electrical generator, and a fuel factory, all at the same time. For decades, the complexity of managing material degradation and real-time fuel breeding led to a cynical running joke in the scientific community that fusion is the energy of the future and always will be. But the timeline for this technology has accelerated. In December 2022, at the National Ignition Facility in California, humanity recorded an event that moved fusion out of the realm of theoretical physics. American scientists used an approach called inertial confinement fusion. They placed a perfectly spherical, diamond-coated fuel pellet the size of a peppercorn, filled with frozen deuterium and tritium, inside a tiny gold cylinder called a holrom. They fired 192 of the world's most powerful lasers at the inside of the gold cylinder simultaneously. This instantly vaporized the gold, creating a massive bath of X-rays. These X-rays bathed the fuel pellet, causing its outer diamond shell to explode outward.
In response, the inner fuel was driven inward, crushing it at hundreds of kilometers per second. For a fraction of a billionth of a second, the implosion generated conditions found only inside a detonating nuclear weapon or the core of an exploding supernova. The result was ignition. For the first time in the history of science, the fusion reaction produced more energy than the lasers used to trigger it. This single moment proved that a controlled fusion reaction could achieve a net energy gain. It demonstrated that the fundamental physics of terrestrial fusion were sound. This milestone triggered a shift in momentum away from massive, multi-decade international projects like the ITER reactor in France. An unprecedented wave of private capital is now flooding into a new generation of commercial fusion startups. Spin-off companies from institutions like MIT are abandoning old Tokamak designs to pursue more compact, agile architectures. These companies are utilizing a material called high-temperature superconductors. By wrapping their reactors in a specialized tape called REBCO, rare earth barium copper oxide, they can generate magnetic fields vastly stronger than anything used in previous decades. This allows engineers to drastically shrink the footprint of a functioning fusion reactor, from the scale of a stadium down to the size of a moving truck, potentially cutting construction times from decades to years. Other startups are abandoning the Tokamak concept entirely, experimenting with pulsed magnetic fields and supersonic plasma rings. Some designs even aim to harvest electricity directly from the magnetic recoil of the expanding plasma, skipping the need for traditional steam turbines and boiling water.
The sector has transformed into a high-stakes engineering war. Dozens of companies are racing to be the first to move fusion from the lab to the electrical grid. America is pursuing this technology with such urgency because the geopolitical and economic stakes of this energy source are absolute. China is currently outspending the rest of the world in state-funded fusion research. They are building state-of-the-art reactors at breakneck speed and running their facilities 24 hours a day. They recognize the leverage that awaits at the finish line. The 21st century is set to require an immense increase in power. Between the electrification of transportation, industrial manufacturing, and the energy demands of artificial intelligence data centers, the global grid is under mounting pressure. Wind and solar are crucial, but their output is intermittent. Traditional fission is powerful, but remains politically difficult to scale. Fusion offers a different path. It is the only technology capable of providing a constant, incredibly dense, zero-carbon supply of baseload power anywhere on the planet. This is the most essential engineering project ever attempted by our species. The first nation to commercialize fusion secures a degree of energy independence and geopolitical leverage that has no modern equivalent. We are watching a desperate race against time, material limits, and our own ingenuity.